These are the notes that we did on Thursday. We're still in 4.4. We moved past the accumulation one. We're going to do that one on Friday. So we're on 4.4. I don't know what you call it, D probably, but there's a page in your notes that just has this single integration problem on it that we need to cover before we move on to our next section. And our next section is going to be an old topic with a new twist, working some more with position, velocity, and acceleration models. So before we do that, we need to figure out how we can tackle the fact that we do not know what the antiderivative is for the absolute value function. If I were to ask you what's the antiderivative of x, you say x squared over 2. But when I ask you what's the absolute values antiderivative, we get kind of stuck. This is how we tackle that. First of all, you could go to your calculator, and your calculator can handle it. If you just hit your Math 9, and it's going to pop up your integral, and if you enter your bottom limit, your top limit, and then to get the absolute value, you hit your math, and you head over to num. Absolute value bars pop up, type the function in, dx, hit enter. It'll tell you that the answer is 4. But more importantly, it's what does that answer represent? The area between the curve and the x-axis of this function that we call f of x. So let's take a look at what the graph of this function looks like. In order to do that, I like to find its x-intercepts by factoring. I know it's a parabola because it's a quadratic equation. I also know it hits the x-axis at 3 and at 1. It opens up. I know it's going to hit at 0, 3, so I do know it's going to come around like this, swoop down somewhere, I don't really care how far down, and then go back up. And I'm integrating the absolute value of it. So what that means is, everywhere that this went negative, what my calculator does when I hit these absolute value bars is it really pops it up here. And so the area that I just found to be 4 is this, the positive value of this, and this right here. So that green stuff adds up to 4. And on my calculator, that's fine. But what if I didn't have a calculator? How can I get this 4 by hand? And years ago when I was in high school, I didn't have a calculator to tackle this. I had to figure out how can I combat this absolute value issue. And what we do is we break it up. We take the integral and we say from 0 to 1 right here, the absolute value bars are not necessary. Because this is positive, I don't need absolute value bars. If I want 8, I just say 8. I don't need to say absolute value of 8. So in the 0 to 1 interval, I can just remove the absolute value bars and it won't matter numerically. But in the next interval, from 1 to 3, all the y's went negative. The absolute value command made them positive, but I need to do that without an absolute value command because I need to take the antiderivative and I don't know what the absolute value's antiderivative is. So I've got to think about how I'm going to do that. This point down here, let's say it's at 2. I can actually figure out exactly what it is. Let's get an exact one. That would be 4 minus 8. It's at 2, negative 2. What I want to happen right here is to pull it up and have it be up at 2. I want those y's to be positive. So how I counteract that is I say, all right, I'm going to have this integrand be x squared minus 4x plus 3. But in order to pop it up, I'm going to take its opposite, or subtract it. That way, if I did the minus 2, it'd throw me up here on the graph. So our our process for taking an absolute value integrand and being able to do it by hand is to find where the function goes negative below the x-axis and pop it up by doing subtraction instead of addition. Now, if I had to, I could do the antiderivatives of each of these, etc., plug in the 1, plug in the 0. I don't want to do it because I know you'd know how, but if we did, we could get the 4 without using our calculator. And the reason we're doing that is because when we start working with our straight line motion again, and again by straight line motion, I mean something's going to be moving either left and right or just up and down. And we're pretty familiar with our position and our velocity and our acceleration models. And we know that the derivative of position is velocity and the derivative of velocity is acceleration. Well, integration undoes derivatives. So although you do derivatives to go that way, we integrate to move up the hierarchy. So if I'm being asked to find the velocity when I'm given the acceleration, I need to take the antiderivative or the integral. So I would say that my velocity model can be found by integrating my acceleration model. The integral of acceleration is velocity, and then I do my antiderivative, 4t squared over 2 minus 6t plus Carl. And remember, for an indefinite integral without those limits, you do need to have your constant of integration. So right now, what I'm saying is the velocity function has an infinite number of possibilities. I could put any constant at the end, and its derivative or its acceleration function would be 4t minus 6. However, they locked me into one particular velocity model. It's the one that when I put in a 0 for t, my velocity is exactly 3. What that does is it allows me to find my arbitrary constant of integration. So when I put in a 0 for t, my constant has to have the function output of 3. So this is 0, this is 0. What that tells me is 3 is my c. So my velocity model is 2t squared minus 6t plus 3. Next, I want to get the velocity model on this one. So again, I know that to go from acceleration back to velocity, I integrate my acceleration function with respect to time. The antiderivative of sine, remember we go sine, cosine, negative cosine, sine. And sine's antiderivative is negative cosine. So I'll have a negative cosine t plus 2t squared over 2 plus c. That's my velocity model, and there's an infinite amount of them that will yield this acceleration model, but only one of them goes through this point. So when I put in a 0 for t, my velocity with respect to time is 5. So a 5 has to come out when I put a 0 in for t. That'll be plus 0 squared or 0 plus c. Cosine 0 is 1, yielding a c of 6. So I'd wrap this up by saying my velocity model is negative cosine t plus t squared plus 6. Bam. Now, why are we working with this absolute value concept and how to get the velocity? It's because both are in a formula regarding either displacement and or distance traveled. Now, here's a really easy question. If I started here and I went east for 80 miles, and then I stopped and went west straight back for 60 miles, my displacement is utterly obvious, right? Displacement is your distance from your start. So let's go write that in case you didn't know that. How far you've been displaced, distance from your start. At the end of this, I'm really only displaced 20 miles. I'm 20 miles from my home base. My total distance traveled is the 80 that I went east when velocity was positive, and then the 60 that I went west when the velocity was negative, but it didn't matter because it's like the odometer on my car. It doesn't mean that when I go home today, it's going to remove miles, even though technically that velocity would be considered negative because I'm going in the opposite direction. I still kind of just ignore the fact that that would be negative, and I say I went 140 miles. That is super easy. However, it's easy because we're talking about position. I gave you a distance or a position and I asked you questions about position. But that's not what's going to be happening. We are going to be given the velocity and being asked questions about position. That puts it at a whole another level. But before we get there, let's answer this question. Can displacement ever equal distance? Could these be equal? And the answer is yes, obviously. If my velocity is always positive, then my displacement, had I just continued going this direction and gone 60, then I'm displaced 140 and I have traveled 140. And somebody asked in one of the classes this morning, they said, well, what about if it's negative the whole time? And kind of think about it. If I went back 10 and then back 20, my displacement is actually negative 30. I am 30 to the left, where my total distance traveled is 30. So when they're both negative, they're actually opposites. They're not the same. So the answer truly is when the velocity is always positive, then total distance can equal displacement. So think about how we're going to get from our velocity model. I should write that, I just erased it. How am I going to get from my velocity model back to something that'll give me displacement or distance? Well, both of these are questions about distance or position. They are both labeled, for instance, in miles or feet or meters or whatever my unit of measure is. And so if I'm given my velocity model and I need to feet per second or miles per hour and I need to go back to just miles or just feet, I need to integrate to do that. So you'll see both of these formulas are integrating the velocity model. The fine difference between them is commonsensical, if that's a word, because think about me taking steps. If I take 5 steps forward and then 2 steps backward, my displacement is 3. I want these 2 steps that I am going backwards when my velocity is negative. I want them to count as negatives. I want it to be 5 plus the 2 I went backwards for 3. But when I ask you the total distance traveled, kind of like how many steps did I take, it becomes 7. I want these ones where the velocity is technically negative to be counted as positives. So that's why you see an absolute value bar in our distance model. We want every time we are going backwards, like when I go home today and I live in Malacca, I want that to count as a positive 30 miles on my odometer. However, my displacement during the day will be 0 because I came to work and then I drove back and I'm displaced 0 when I'm all done, but my total distance is 60. So again, they're never equal unless I never change direction. Then they are equal. As long as my velocity is positive, I will never have an issue. But otherwise, distance is always going to be greater because we're going to take all those negatives and count them as positives. So let's go take a look at an example. So here's my velocity model given by the quadratic equation t squared minus 7t plus 10. Right here you can see the graph of v of t. So this would be called t. This would be v of t. It's a graph of all the velocities. This is t. This is actually the absolute value of v of t. So it took all this negative velocity and put it above the t-axis. We are going to answer a couple questions about this. The first one we're going to answer is about displacement. Displacement's easier. My displacement would be this. And we don't want to memorize formulas, we want to think it out. I'm given the velocity. I want to go back to a question about distance and displacement, aka position type question, so I know I need to integrate my velocity function. I'm on a time interval from 1 to 7, it said up there. And then I decide, do I need the absolute value bars or not? For displacement, do I want those negatives to count? And the answer is yes. So this is truly it. I didn't memorize a formula, I'm thinking it out. So I'd have t squared minus 7t plus 10 dt. Could I do that by hand? Sure. All I would do is my antiderivative, evaluated from 1 to 7. I put the 7 in, then the 1 in, and subtract them. I'm just going to go dot, 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 because that's really not what we're working on today. So when you get to here, go ahead and math 9. So if you take out your calculator and math 9, your displacement, and you really should take out your calculator and do that so you get used to it. You're going to integrate from 1 to 7 this function. You'll get the answer of 6. Let's talk about what that 6 means. What it means is I'm 6 from wherever I started. Usually we assume that you've started at 0, 0, so you'd be sitting at 6, but sometimes what they'll do is they'll tell you at time 1, you are at negative 4, and then it'll say, what is your position at t equals 7? Well, my position is going to be wherever I started plus my displacement. So at 1, I was already 4 backwards, and then I got displaced. And we just said that this was 6. So I'd say my final position in that scenario is at 2. So my displacement is 6. But if it talks about your final position, you have to take into account where you started. And if you didn't start at 0, 0, then you just say it's where I was plus, some people call this net change in distance, but plus my displacement. So similarly, but not the exact same, how about my total distance traveled? So let's do total distance. I'm not going to memorize the formula. If I'm given a velocity model and I want to go back and answer a question, basically if I'm given feet per second and I'd like to get rid of that per second and have an answer in feet, I need to integrate to remove that rate of change. So my total distance is going to be what I get when I integrate my velocity. And again, I'm on a time interval from 1 to 7. But the difference here being every time I was moving backwards and my velocity was negative, I want it to be counted as positive. So that's why I put the absolute value bars on there. And if I'm allowed to use my graphing calculator in my Math 9, which most of the times you are for this one, then you're just going to go to your calculator, you're going to integrate from 1 to 7, t squared minus 7t plus 10, absolute value, so you have to use your Math num option, and it's going to give you a 15. It shouldn't be a surprise to you that that's quite a bit bigger than the 6 because we were going backwards for the whole interval from 2 to 5. That's a lot of time as going backwards where it was counted negative in this one and positive for my total distance. The harder thing with this kind is how would you do it without your calculator? Because again, we have no antiderivative for the absolute value function. And if we didn't have a calculator, we wouldn't be able to look at the graph either. So really what you need to do if you're going to do it by hand is you need to figure out manually where did that go negative so that I can make it positive. So we factor our velocity. Oops, my smartboard seems to have locked up here for a second. Hopefully I'll be able to finish. Yep, there we go. So we did this in another chapter. We're looking for where our velocity is 0, which is at 2 and at 5. And I'm looking over a time interval from 1 to 7. I had a closed time interval. At 2 seconds in, I was stopped. At 5 seconds in, I was stopped. And you might say, I can see that from the graph. Hello. But keep in mind, what if you weren't able to look at a graph? You'd have to analyze it more analytically like this. So in this interval, this product would be positive because I'd have a negative times a negative. At say 3, I'd have a positive times a negative. At say 6, I'd have 2 positives. So now this tells me without a graph that this right here is when I was moving backward. And in displacement, I want that to count as negative. But for total distance traveled, I do not. So I can't use the absolute value symbol because I don't know its antiderivative. So I wouldn't be able to tackle that by hand. What I do is I say I'm going to integrate from 1 to 2. And I'm just going to use v of t here because I don't want to write this polynomial out a zillion times. But from 1 to 2, it was positive anyway, so why bother with the absolute value? But from 2 to 5, my velocity went negative, and I want it to be positive without absolute value bars. So if I just subtract off that negative, it'll pop it up and make it positive. In addition, I'm now going to integrate from 5 to 7, and I can just add that on because those were positive anyway. This I could do by hand because remember, my v of t is really this polynomial that I can easily find the antiderivative of. T cubed over 3, it's this one. I would just have it strung out 3 times. I put the 2 in and then the 1 and then subtract. The 5 in and then the 2 and then subtract that. And I could do it. It's a lot of manipulation and a lot of arithmetic, but it's doable. So if I did that, dot, 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 and took 10 minutes, which I don't want to waste, I would get a 15 that would match my calculator answer. So there was no need to do this one in class because everybody was getting it. So if you were absent, we didn't do that one. That's one from your book. The homework for this section is in the 4.4 work packet. I think it's the last one in there. We're a little out of order, but we'll take care of it all by the end of the week. So if you open this up, the assignment is 1 through 5. These two, go ahead and use Math 9. So just go ahead and set them up. You're just going to be doing your displacement and your total distance traveled. So just go ahead and Math 9. On these, same thing, you can go ahead and Math 9 when you're doing your homework to wrap these up, but keep in mind the acceleration was given. So before you can use your formula for displacement and go from 0 to 3 of v of t dt for this one right here, you're going to have to integrate your acceleration, and it's like the one we did in the notes. The one I really want to talk about with you is number 5. So we did number 5 in class. I forgot to erase it, so I'm going to take it off here. So homework for you will be 1 through 4 because we're going to do 5 right now. What we have here is a rocket that's been blasting off, and it goes up. Here it is, and it's got this propellant, and it's got an engine that's shooting it upward very fast, and then what happens is it says the engine burns out, but the rocket will continue to go up. It'll just go up slower. Then at some point, gravity is going to take over, and the rocket's going to start to fall, and it's going to fall faster, 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 but then a parachute pops open to slow it down before it hits the ground. Its velocity is being modeled over time in feet per second. It's a piecewise function, so go change that to v of t. What this piecewise function says is that from 0 to 2, it's the parabola 50t squared, which hits at 0, 0. And when you put a 2 in here and square it, you get a 4. 50 times 4 is 200. It's a parabola that opens up because the 50 is positive. So that right there is modeling the velocity in the first 2 seconds. Then I've got a linear model for the velocity. And at 2 seconds, if I put a 2 in right there for t, it's at 200. If I put a 15 in to see where to end that model, 260 minus 30 times 15 ends up being negative 190. We did it in class today. But before I connect these dots, I'd really like to know where it hits the t-axis, because that's when the velocity is 0. That would represent this right here. That's that turning point where gravity takes over and sends that rocket back to the Earth. So we have to do 260 minus 30. Sorry, Mr. Janan came to the door. I had to pause the video for a second. So I kind of forgot what I was saying because we were chatting about supper, and supper's super important. What was I doing? Oh, okay. I was going to find where my intercept is on my t-axis. So if you do 260 divided by 30 to solve the linear equation, you get 8 2/3. So when I connect these, I'm going to head right through 8 2/3 on my t-axis. I'm going to label that. And then once t is greater than 15, my model becomes a parabola again, but this time it opens down, and at 20, it's going to be 0. So it goes like that. So keep in mind what you're staring at. I'm going to make this one red. And let's go even label these. Let's call this blue. Call this one green. Then I don't have to rewrite them a bunch later. And this one red. So I have 3 functions that are giving me my velocity as this rocket starts and then lands. Let's take a look at what's going on here. This blue one right off the bat represents the rocket being shot up and up and up and up and being forced up faster and faster and faster. Because you can see over here the velocity is increasing, and it's increasing at a faster rate because you can see the slope of the tangent lines are also getting steeper. So the velocity is increasing at an increasing rate. So let's write this. This is going up fast. Then what happens, remember, in the situation is the motor cut out. The rocket continued to go up, and this does represent right here the rocket going up. The velocity is positive. It's just going up slower because gravity is pulling on it. Then it reaches its highest point, and gravity just finally wins and starts pulling it back down. So this right here actually represents where it's at its highest point, and gravity takes over, and then our velocity becomes negative because it starts to fall again along this. It falls faster and faster and faster because gravity is yanking on it, and it's heavy, so it's going really, really fast. Right here you can anticipate what happens. That's where that parachute deploys. And when that parachute deploys, it slows it down. It's still falling, though. It's really hard to look at a graph that's increasing and say that the rocket is falling. But remember, I'm looking at a graph of the velocity. The velocity is still negative on red. It's just less and less so. So once that parachute pops open, right? I don't know how to draw a parachute. What it does is it slows the fall down. So now we can answer the questions. For how many seconds did the engine burn? 0 to 2. Then the engine stopped. It stopped, but the rocket continued to go up. And it says, how fast was the rocket going when the engine stopped? 200 feet per second. When did the rocket reach its highest point? Contrary to popular belief, it's not there. That's when the rocket lost power but continued to go up until, because again, velocity is positive here. It is going up. It's just going up slower because gravity's yanking on it. So it reached its highest point at 8 2/3 seconds. And if I wanted to know how high it was, then I'd take my feet per second and get rid of the seconds by integrating. So the area under this curve right here represents how high it was at its highest point. Didn't ask that, but it says, when did the parachute pop up? At 15 seconds. How long did the rocket fall? It was falling along this entire green thing until the parachute opens, which would be 6 1/3 seconds. How fast was the rocket falling when this parachute opened? And we had a -90, but we don't put the negative on there because fast implies speed. Speed is the absolute value of velocity, so we say it was going 190. Again, the fact that it was negative just means it was falling. When was the rocket's acceleration the greatest? Acceleration, remember, is the slope of the tangent line. You can kind of think of it with the rocket. It's going its fastest right when that engine burns out because that's propelling it up. That's right here. Technically, we shouldn't say at 2 because at 2 it stopped very briefly, but it had to stop to fall. So we would say right up to 2, or you could say it's actually the limit as t approaches 2. But anyway, we'll say 2, but it's really 1.9 repeating. It's really kind of a limit as t approaches 2. Assuming that the rocket does land, we won't do I. This is where we tie in what we did today. Assuming the rocket lands, I suppose barring any unforeseen, like a plane coming and blasting it or wind taking it away. That'd be quite a wind. Assuming it lands, how far does it travel? So this is a question about distance. I have been given velocity models, so I know I need to integrate them. It's a question about total distance, not displacement. Displacement's a no-brainer on this one. If I wanted to know how far I was from my start, if that thing landed, my displacement's 0. I started on the ground, it landed on the ground. But how far did I go? Assuming these rates that they gave me over here, I'm going to have an integral. I'm going to integral for the first 2 seconds under the blue curve. So I'm just going to write blue dt. Then from 2 seconds to 8 2/3 seconds, I'm going to integrate under the green dt. And again, I could write 260 minus 30t dt, but I don't want to. Then from 8 2/3 seconds to 15 seconds, let's go do that, 8 2/3 to 15 seconds, I am still green. But it's under the curve, and I can't put absolute value because I want to be able to do it by hand. So instead of adding those negatives, I will subtract them, and consequently, it'll count this right here as distance traveled. Even though its area or its integral is negative, if I can subtract it, it'll pop that up, and it'll give me that. Then, oops, I can't go, yeah, I can go from 15. And then from let me erase that up. I lost my train of thought here. And then from 15 to 20, I'm under the blue, aren't I? Nope, red dt. But again, I'm going to have to subtract that one as well because it was below the x-axis. If I wanted to know how high it was at its highest point, I would have integrated these two. And that would tell me its maximum height, which makes sense because it gives me its maximum position. And position's derivative is velocity, and maximums of functions occur where the derivative changes from positive to negative. So a lot of tie-ins with this problem. We are done. The assignment is 1 through 5 on the straight line motion revisited worksheet. You have a good one. Talk to ya later.